Okay, I'm just going to run through a real quick review of Chapter 10, getting ready for the test here. I want to run through some definitions first. We know what a circle is. It's all the points that are equal distance from a center point. The radius, of course, is the distance from the center to the segment itself is the radius, but the distance is also called the radius. The diameter is a distance all the way across going through the center of the circle, so it's always double the radius. The secant. Secant line is when you have a line that crosses a circle twice. So if you look, you got a point here, you got a point here, it crosses the circle twice. By the way, this isn't listed over there. We're going to talk about this more in just a second. But if you just look at just the segment, so if you look at that segment right there, that is called a chord, right? So the secant line is the line that keeps going both directions. The chord is just the segment that I just outlined in red right there. Okay, a tangent line. So a tangent line is when you have a line that just touches the circle in one spot. So just touches that point right there. The point where they touch is called the point of tangency. So those are some definitions we ought to be familiar with hopefully by now, but just a quick review over those. When you have two circles, you can have common tangents. And what all that means is you can have a tangent line that touches both circles. So these two are both tangent lines. They're common tangents. Both those lines touch each circle once. It's not the best drawing, but theoretically. Hey, those are called the external tangents. If you picture in the middle here, if I draw a line from the center to the center, a tangent line that does not cross that center, if I go from the center of the circle to the center of the other circle, if it doesn't cross that, it's considered an external tangent. If it does cross it, I could draw a tangent line that comes down and touches there and then touches there. See, it crosses that green line. Okay, that means it's an internal tangent line. So that's just a couple of definitions. The blue ones are internal tangent lines. The red ones are external tangent lines. So those are common tangents. Okay, with tangents, we went through a couple of theorems. One was this: if you have a tangent line like I have up here, and there's a point of tangency, and you notice how the radius goes up to goes from the center to the point of tangency, that will always form a 90-degree angle, always. The other theorem we had is if you have a point on the outside of a circle and you draw the tangent lines, right? There's one, there's the other one. Okay, those two, we call those tangent segments because they're not lines. But those segments will always be congruent also. So those are the two really big main theorems that we went through with tangent lines. Here's some examples. If you look at this first one, and you'll have to forgive me, the directions got cut off here, but the directions on this first one would be asking, is segment ST a tangent? Like that's what it would be asking us. Well, the way we can tell that is, the question we're going to ask is that a right angle? That's what we want to find out. Well, we know how to check for that, right? That's a triangle, and we can check to see if it's a right triangle. So I would check, does 35 squared plus 12 squared, does it equal 37 squared? If it does, that's a right triangle. That means those two are the tangent line and the radius are the line and the radius are perpendicular, which makes it a tangent line. We'll see 35 squared plus 12 squared is equal to 1,369. 37 squared equals same thing. Hey, so it is. So this checks off. So is it a tangent line? We would say yes. This problem's a little bit different. This would be asking us, it would tell us that AB is a tangent. That's given to us. And what is R? Try to find out what the radius is. Well, if AB is a tangent line, and this is the radius, we know that has to be a 90-degree angle. So we can use Pythagorean theorem again, right? We know that A squared, so we're going to take that leg and square it, plus take the other leg of the triangle, R squared. That has to equal that entire segment squared. So R plus 50 squared. Okay, now we're just trying to solve for R. I want to show you, normally I just leave this problem, but I want to show it to you really quick because there's a common error we make here. Right, we square 80. Okay, you got to be really careful over here. Sometimes we just want to square the R and square the 50. You can't do that. Either we have to go R plus 50 times R plus 50 and do the whole, distributive property, FOIL, Or the shortcut is you square the first term, r squared. You square the last term, 50 squared is 2,500. But in the middle, you have to times those two together and times by 2. So 50r times 2 is 100r. This is the same thing you'd get if you did this up here. So just be careful when you square. That's a binomial, right? It has two terms. You've got to remember that's going to have the middle term right there. Okay, let's just finish solving this. We're already to here. So I'm going to minus r squared from both sides. And this works out nice because it goes away on both sides. So now I don't have to worry about a quadratic anymore. I'd have to solve this equation. And I'm just going to leave it at that. You guys can go through and solve that the rest of the way if you want to. I think it comes out maybe to be 39. Hey, this last problem, again, the directions are left off, but it would say, you know, solve for x, given that RS is a tangent line. So we know RS is a tangent line and RT is a tangent line. So that means we know those are congruent. That's what has to happen. So 3x plus 4 has to equal 28. Oh, sorry, 3x plus 4 has to equal 28. You would solve that equation and you'd have your answer. Those are the main theorems from that first section from 10.1. Okay, 10.2, central angles and arcs. Okay, so our theorem here was, remember, first of all, an arc is part of a circle. We have minor arcs. That's a minor arc. It's less than half the circle. So arc AB is a minor arc. Or you have major arcs. Major arcs are more than half, so we could also go between A and B. When you name a major arc, just remember, major arcs, you always use 3 letters. Right, so it starts at A, it passes through D, and it ends at B. So arc ADB, and that's a major arc. Hey, the idea here is really simple. All it says is, if I can find the measure of the central angle that intercepts that arc, it's the same as the arc. So this measure right here is the same as the measure of that arc right there in degrees. Real quick example of that. Let's say up here I was trying to find the measure of arc GH. Okay, so actually let's not do GH. Let's change that. Let's do the measure of arc FG instead. Okay, so first of all, identify the arc. Here's arc FG. Identify the angle, the central angle that goes with it is that angle. If I can find this angle, I'll know the measure of that arc. Well, to find that angle, I can go 360 minus all these other angles, right? I can subtract off all of this over here. So minus 40, minus 80, minus 110. So that'd be 120. That'd be 240. So 240 minus 110. Is that 130 degrees? So the measure of FG is the same as the measure of that arc right there, which if I did my math right there is 130 degrees. So the measure of arc FG is 130 degrees. Okay, one thing really quick, I didn't mention this on that previous page and I talked about the theorems from this, but we also talked about in that section on 10.2 that if I have two arcs in the same circle, so that red arc and that red arc, if their central angles are congruent, then those two arcs will be congruent, which means that doesn't mean just that they have the same measure, right? Those are both 80 degrees, but it means that they're actually the same length. Okay, they have the same length, which should kind of make sense. If the central angle is the same and the circle is the same size, they have the same measure. Just be careful. On this one, I have two different circles, right? The measure of that arc in degrees is 90 degrees. The measure of that arc is 90 degrees, but those are not congruent, right? This circle is bigger, so that arc is longer. So the circles have to be the same size. It has to be the same circle, two arcs in the same circle, or the circles have to be the same size. Here's an example, right? It shows us that that radius is equal to that radius. So the circles are the same and the angles are the same. That's 95 degrees, that's 95 degrees. That means those arcs are congruent. So are the arcs congruent? This would be a yes. They're in the same circle and their central angles are equal. This would be a no. Their central angles are equal, but one circle is bigger than the other one. This would be a yes because the circles are the same size and their angles are congruent to each other. Hey, chords. Here's all the theorems on chords. So we had three main ones. The first one is, if you have a circle like this one, and I have these two chords, there's one, there's the other. If the chords are congruent, that means the arcs are congruent. So if the chords are congruent, then the arcs are congruent. if you have two circles that are congruent, so let's go down here. Let's say these two circles are congruent. That's given to us. So the circles are the same size. They're congruent to each other. If the chords are congruent, the arcs will also be congruent. And the converse is true. If the chords are congruent, then the arcs are congruent. So that's our first theorem. The second one is this, is if you have a chord that's the diameter, it passes through the center, and it's perpendicular to another chord, it always bisects the chord and it bisects the arc, right? So it has to be the diameter and it has to be perpendicular. If that's true, then it bisects the chord and the arc. The converse is also true. And what I mean by that is if you have a chord that's perpendicular, so it's perpendicular, and it bisects the chord and the arc, that means it has to be the diameter. So that has to be the diameter. Okay. So you can look at that both ways. If it's a diameter and it bisects the chord and it's perpendicular, it bisects the chord. If it bisects the chord and it's perpendicular, then it's the diameter. Okay, our last theorem we went through with chords was this. If I have two chords that are equal, say that chord is equal to that chord, if I measure the distance from the center, from there to there, and from there to there, that distance will always be equal. And remember, that distance is always the perpendicular distance. The converse is also true. If the distance is equal, so if that distance equals that distance, that means that that chord will be equal to that chord. Okay, they'll be equal to each other. So let's look at some examples with that. Again, the directions are left off here, so we'll have to kind of improvise a little bit. But if you look at this first example, maybe it wants us to find what is the measure of this arc right here. Okay, if you look at it, first of all, the two circles are congruent, and we know that because their radii are congruent. We also know that the chord, this chord, right, is congruent to that chord. Well, that means that that arc is congruent to that arc. So this arc has to be 80 degrees. Okay, let's look at this example over here in the upper right-hand corner. Let's say it asks us to solve for x, find out what x is equal to. Okay, so if we're trying to solve for x, we look at this. Well, we know this is a diameter. It passes through the center, and it's perpendicular. That means it bisects that chord. It also bisects that arc. So first of all, if this side is 5, this side has to be 5. But let's say we're trying to solve for x. I know that that arc has to equal that arc, so all I have to do is go 9x equals 80 minus x. I'd solve that equation. I'd get my answer. Let's see. Let's look at these bottom two. Let's see. On this one, the bottom left-hand corner, let's see if we can solve this. So if we know that, let's see, we know it's a diameter, passes through the center, and it's perpendicular. That means those have to be equal. So this side has to be 7. We also know that those two arcs have to be equal. So I could solve for x by setting those equal, 11x equals 70 plus x. So I'd solve that. I think it comes out, x comes out to be 7 on that one. Again, there'd have to be some given information on this last problem. Look down here on the right side over here. Like we're missing some information here. But let's say it told us that arc QR was congruent to arc ST over here. So let's say we knew that those two were congruent. Well, if they're congruent, that means their distance has to be from the center has to be congruent. So we could set that up. 2x equals 5x minus 9, and you could solve that problem from there. You could work it out and solve it. There was another type of problem. If we solve this, it comes out to be x equals 3. So if I come back up here, if I plug 3 back in, this comes out to be 6 right here. This part comes out to be 6 also. What if let's say it told us that this side was, let's say it was 8, and that side was 8. Let's say it asks us to find the radius. I just want to remind you of this little trick. So if it wants us to find the radius, if I know what those two are equal to right there, both equal to 8, I know this segment's equal to 6. What you can do is you can draw the radius going that way and make a right triangle. And now I know that side, I know the two legs. I know 8 squared plus 6 squared would have to equal the radius squared, and you could solve it that way. So just remember that little trick. If it does ask you to find the radius, draw the radius going this way so you can form that right triangle. I'll outline it in red. You want to draw the radius going that way. That way you can form a right triangle and use the Pythagorean theorem to go through and solve that. Hey, inscribed angles. Inscribed angles are pretty simple. If I have an inscribed angle, don't mix them up with central angles. Whatever this angle is, let's say this angle is x degrees, then this arc would be 2 times x degrees. So the arc that the angle intercepts is always double the angle. If you have a triangle that's inscribed inside of the diameter, so the diameter is one side right there, that means this arc is 180, which means this angle always has to be 90. You don't really have to memorize that, but just so you know, if you got a diameter and you inscribe a triangle inside a half a circle, inside a semicircle, that angle will always have to be 90 degrees every time because it intercepts this arc, which is 180. The other theorem we went through was this, is if you have a polygon, a quadrilateral, inscribed inside of a circle. Inscribed means it has to be touching the circle. We talked about how the opposite angles are supplementary. So let's number this off, A, B, C, D. So angle A and angle C their measures have to add up to be 180 degrees. Should put the measures there, I guess. And B and D, the measure of angle B plus the measure of angle D, also have to add up to be 180 degrees. Okay? So opposite angles have to be supplementary. So this angle and that angle have to add up to be 180, and that angle have to add up to be 180 degrees. Here's a couple of examples. This one, right, it wants me to find the measure of angle T first. Angle T is right here. Well, I know that arc is 48, so I'd cut it in half. It'd be 24 degrees. It wants me to find the measure of arc QR. This one's a little trickier, right? QR is up here. There's no angle that goes with that. But so you kind of have to look at what else I know. I do know, if you look over here, that this one, right, that's 50 degrees, which means this arc right there has to be double that, 100 degrees. Well, the whole thing, that's half a circle, has to be 180. So if this one's 100, I'm trying to find this one up here. I'd go 180 minus 100, so that'd have to be 80 degrees. So it can get a little bit tricky, but the idea there is the same, as inscribed angles are always double the, inscribed angles are half of the arc. The arc is double, measure of the arc is double the angle. Hey, these bottom two examples, if you look at this angle right here, right, that angle goes with an arc that's 180 degrees, so the angle has to be half of that. So 2x has to equal 90 degrees. You could solve that from there. Okay, on this one, you've got a quadrilateral inscribed inside of a circle. That means the opposite angles, that one and that one, have to add up to be 180. So z plus 80 equals 180. And that one plus that one have to add up to be 180. So y plus 120 have to add up to be 180. Okay, when you find that. Okay, just a couple of theorems on angles. One is, if you have a tangent line and a chord, it's like an inscribed angle. That angle, we do it in a different color, that angle right there will be half of the measure of that arc. Okay, just like an inscribed angle. If you have something like this, where two angles cross on the, two chords cross on the inside of the circle, if I take this arc plus this arc and divide it by 2, or take half of it, it's equal to this angle right here. So let's number this off. Let's say this arc is x, this arc is y, and the angle is z. What the theorem says is if I take the two arcs, x plus y has to equal, take half of that, or divide it by 2, that has to equal the angle, which is z. Okay, so that arc plus that arc divided by 2 equals that angle. If the two lines cross on the outside, instead of adding the arcs, you subtract the arcs. So let's we'll call this arc X, we'll call this arc Y, and this arc Z. So if the angle's on the outside, we take the big arc X, instead of adding, we subtract the little arc Y. You take half of that, or divide it by 2, and that has to equal the angle. So if they cross on the inside, you add them and divide by 2. If they cross on the outside, you subtract them and divide by 2. So here's a couple of real quick examples. The measure of angle 1 it tells us the line is tangent to the circle. Line M is tangent to the circle, sorry. Find the measure of the red angle or the red arc. So in this case, we want to find this angle right here. Well, that arc is 130, so that angle has to be half of that, 65 degrees. We're going to skip past that next one, look at these bottom two examples. So if you look at this first one, I'm trying to find this angle right here. Those cross on the inside of the circle. That means I add the two arcs. That angle intersects this arc and that arc. So I go 130 plus 156. I take half of that or divide it by 2. That tells me what x is equal to. So that's what 286 divided by 2, or half of that, and we'd find it. If the angle is on the outside like this one, now instead of adding the arcs, I subtract them. So I go 178 minus 76, big arc minus the little arc, divided by 2, or a half. And that would have to give me what x is equal to. But we're going to skip that last one there. So that's that theorem. Hey, the segments. So now instead of talking about the angles, we're going to talk about the segments. If two chords cross on the inside, remember say x, y, and we'll call this w and z. Okay, then this relationship is true. If I take w times z, that has to equal x times y. So that times that has to equal that times that. If it crosses on the outside, it's a little bit different. So let's number these off again. Let's go x, y, w, z. So if it crosses on the outside, then what we do is we take the outside piece x times by the entire thing. So that entire thing would be x plus y. And that has to equal the outside piece on the other one, w, times the entire thing. That's w plus z. So those are the two relationships we had with chords that cross in circles. So this first one's pretty easy. It crosses on the inside, so I take that times that, 3 times x has to equal that times that, 4 times 6. So what, 3x equals 24, so x would equal 8. This one's a little bit trickier, I guess. We got 2 times x plus 1 equals 3 times 4. We'd solve that from there. This one's, we're gonna skip over that one. I'll just move it out of the way. But let's do this one right here. This one is tricky. So I have to take, now they cross on the outside, so I have to take the outside piece 3 times by the entire thing. So to find that entire thing, I have to add those together. 3 plus x plus 2. And that has to equal the outside piece, x plus 1, times by that entire piece, which would be x plus 1 times x minus 1. Okay, now I've got to solve this ugly, whoops, sorry, I did that wrong. Let me try that again. So take the outside piece, which is x plus 1, times by the entire thing, which would be x plus 1 plus x minus 1. There we go. Okay, let's do a little bit of simplifying. This would be 3 times x plus 5, or if I add the 3 and the 2 together. Over here, this would be x plus 1 times by, if I add these together, the plus 1 minus 1 goes away, so, but I add the x's together, I get 2x. Let's distribute. I get 3x plus 15 equals, distribute here, 2x squared plus 2x. Get that out of the way. Okay, let's finish solving this. This looks like a quadratic. So let's get everything on one side. I've got this 2x squared over here, so I'm going to move the 3x over there. I'm going to minus it over and minus the 15 over. So I end up with 0 equals 2x squared. I minus the 3x, so it would be minus x minus the 15 over. Okay, now I've got to factor that, and I don't care how you do that. You can do the X method. We can do guess and check. You can do it either way. I'm going to do guess and check, but that's up to you. I got 2x and x to get 2x squared. To get negative 15, it could be negative 1 and 15 or negative 3 and 5. I've got to find the right one that works here. I think it's going to be the 3 and 5. Let's try plus 5 minus 3. So check that. That'd be minus 6x plus 5x, which gives me the minus x in the middle. That's my factored form. Again, I don't care how you solve that. You can how you factor it. You can do that with the x method or however you learn that. Okay, so now set each of those equal to 0. 2x plus 5 equals 0. X minus 3 equals 0, and solve those. So I'm going to minus the 5 over, divide by 2. So that's what, negative 2.5. Add the 3 over. So I go all the way back up there, do both of those work. If I plug in negative 2.5, right, negative 2.5 plus 1, that comes out to be a negative. That cannot be a negative because it's talking about the length. So we can throw out the negative 2.5, but the 3 works if I plug 3 in both of those. So. Okay. This problem is really similar to that. I think I'm going to skip that, and we'll move on to this next one. So the last thing we went over was area, circumference, arc length, and area of a sector. Hey, you guys have been doing area forever. Area equals pi r squared. You've been doing circumference forever. Circumference is either 2 pi r or 2 times r is just the diameter. So you could also go diameter times pi. Okay, if you want to find the arc length, that's how long an arc is. For example, you want to find out how long the arc AB is. Okay, the way we do that is you take the measure of the arc over 360 times by the circumference. That gives you arc length. Okay, if you want to find the area of a sector, okay, we take the measure of the arc over 360, just times it by the area. So times it by that pi r squared up there. So those are your 4 formulas, and of course you've seen this. There's a lot of formulas, a lot of theorems in this chapter, and that's why we're going to use a note card. So make sure you have a note card filled out before you take the test. Okay, let me do these last couple of examples here. So let's say we'll find all of them. Let's find the area of that circle first. That's pretty easy. The area of the entire circle, well, the radius is 8. So I go pi times 8 squared, so 64 pi. That's the exact answer. If you want to plug in a calculator, you can get an approximate. The circumference is 2 pi r, so 2 pi times 8. So that'd be 16 pi. Sorry, go back up here. This is square centimeters for area. It's 16 pi centimeters for the circumference. Okay, let's say I just want to find, though, the measure of arc AB. So I want to find arc. How long is arc AB? I want to find that length right there. So I take the measure of the angle, 60 over 360, times by the circumference. So 2 pi times 8. Now there's 2 ways to write your answer. One is the exact answer and one is the approximate. For the exact answer, we would go we would just simplify it. 60 over 360, that reduces. 6 over 36 is 1/6, times by 2 times 8 is 16. And now I'd go 1/6 times 16 would be 16 over 6 pi. You would reduce that. That would be 8/3 pi. And then my measure is in centimeters. That'd be the approximate answer. Now, if you didn't want to do an approximate, if it just asked you to round it off, you could just plug this original problem in your calculator right there and get the decimal. Okay, the last thing is let's find the area of the sector formed by angle APB. So that sector, we're going to find the area of that sector right there. So I still take the measure of the angle, 60 over 360 times by the area. So the area is pi r squared, so pi times 8 squared. All right, again, if it wants me an approximate, I just plug that whole thing in my calculator. If I want to get an exact answer in terms of pi, I would just reduce this. Divide by 0, 6 over 36 is 1/6. 8 squared is 64. So I end up with 64 over 6 pi. And you could reduce that, divide them both by 2. That's what, 32 over 3. 3 pi. We'd measure that in square centimeters. That's the exact answer. Again, you could just plug that in the calculator if you wanted to get an approximate. Hey, the last example I wanted to do, I know this is kind of long, I apologize, but you do have a problem kind of like this on your test, so I wanted to go through it. It says the northern lights are bright flashes of colored lights between 50 and 200 miles above the Earth. A flash occurs 150 miles above the Earth at point C. So here's our point C up here. What is the measure of arc BD? So it wants me to find this arc right here. Well, we just talked about, to find the measure of an arc, I want to find the measure of its central angle. So if I could find that angle right there, or even one of them, because those are equal. So if I could find this angle, then I would double and I'd know that entire angle, which means I know that whole arc. Well, what we have to remember, right, is that if we have this is a tangent line, and this is the radius, it has to form a 90-degree angle. So this is a right triangle. And we know how long this side is, right? This side is 4,150 miles. I also know the radius. I know this side right here, right? That side is 4,000. So if I rail off this side, I got this triangle. Let's focus on this right triangle. That doesn't look very right. We'll pretend like it is. We know this side is 4,150, and we know this side is 4,000. I want to find that angle right there, right? We're looking for that angle right there. So what we can do is use trig. So this is, make sure you label your sides. This is the opposite side. This is the adjacent side. And this is the hypotenuse. So I know the adjacent side and the hypotenuse. So we're going to do cosine, right? Cosine of my angle x equals the adjacent over the hypotenuse. Okay, when you know the ratio and we want to work backwards to find the angle, we do the inverse. So x is going to equal the inverse cosine of 400 divided by 4,150. Okay, so we're going to plug that in a calculator. Inverse cosine of 400, well that's 4,000, I'm sorry. 4,000 divided by 4,150. Okay, it comes up to be 15 point, let's grab the nearest degree. So if we're going out to the nearest degree, it's going to be 15 degrees. So that's this angle right here. That's this angle I'm outlining in black right here. That is 15 degrees. Well, that angle is going to be 15 degrees also. So that entire angle is going to be 30 degrees. Okay, is what that would round off to be. Okay, so that's kind of a cool problem. I liked it because it uses the ideas we have about circles. It also uses trig, which you learned in the last chapter, and kind of combines them all together. And you will have one like that on your test. Okay, make sure you take your time. Make sure you make a good note card to have all these theorems on it. Take your time on the review, and make sure you're ready and prepared for the test on Wednesday. Thanks, guys.